previous snippet I did a calculation of the bias of the valves using my bias probes that I built, but this is never going to be more than an averaging quick and dirty method. So now we're going to go for probably the most accurate method of doing this, which is using the output transformer primaries, and we're looking at initially the voltage drop across them. So here I'm connected to pin 8 of the rectifier and pin 3 of the primary transformer on one side. So what this is in fact doing is measuring the voltage drop across the output transformer windings, and in a minute we'll swap to the other transformer winding to measure that. So we seem to be starting to stabilise at about 12.5. Let me get a pen. So I'm going to mark that down as 12.54. And then we'll move to the other tube, remembering the voltages in here are significant. So as always, being very careful to keep only one hand out. Only one hand being used at a time. And here we can see that the voltage drop is 12.53, so quite close. Now what I'm going to do is just switch off the amp for a moment. Now it only takes, because it's connected in, I've measured the time it takes for the capacitor discharge, and it is quite quick. I'm now going to measure the actual plate to cathode voltage of these valves. So we'll switch it back on again. Again, all in DC voltage. And again, waiting for a moment for it to stabilise. Here I'm going from the cathode pin 8 to again the primary winding of the output transformer pin 3, and here we can see we're settling down now at 307. I'm going to call that 3. I'm going to call that 307. .3. And again, now switching to the other valve, again pin 3, let's get that in there, and pin 8. And again, wait for that to stabilise. Just slightly lower. I'm going to call that 306. 307. 306.9 then. 6.9. Right, now we've taken those measurements, we need to switch off, reattach the leads back to the pin 8 of the rectifier, and again back to pin 3, but now we're going to measure the impedance of the transformer winding. And it's probably better to do this when the transformer has been run, so it's at least a little bit warm. And here we're taking that as 300.5. And then moving to the other winding, again at pin 3. .8. Right. So now with these measurements completed, we can calculate a more accurate bias for the valves. So for this valve we have a voltage drop of 12.54, and we're going to divide that by the resistance of 300.5. Oops. 12.54 divided by 300.5, which gives us a plate current of 0.042 to the third decimal place. And similarly for the other valve, what I would call the inner valve, 12.53 divided by 292.8, which is 43 milliamps, so 0.043. Now we took the plate voltages from the pin 3 to pin 8, the cathode to plate voltages, and we got around about 306.9. So if we multiply those plate currents by the voltages, we will end up with the dissipation in watts. So we've got, that last one was 0.043, so we multiply that by 307.3, which equals 13.15. If I divide that by 14, the maximum dissipation, we get it running at 94%. And then we go to 0.042 for the other valve, and that was at 306.9, which equals, oops, wrong, dividing instead of multiplying, 6.9 times 12.88, got 12.9, and that one is running at 92%. So there are the calculations. I don't know if you can see that actually. No, you can't see that particularly, can you? Oh yeah. That I've come up with. So again, running at an average of 93% across the two tubes, which is reasonable for a cathode biased 6v6 pair, but again I would like to get it around under the 90 really, so maybe looking at increasing the cathode resistor a bit. So increasing the value of this resistor to accommodate a lower wattage of dissipation.